So, good morning and welcome to the fifth lecture on discrete math. Today, what we are going to discuss is the third home assignment. For this home assignment, I will give some basics, and it will be a short exercise in representing graphs in Python. This will be the main idea for that, and we'll give some links, and of course the assignment will be published on the web. So the deadline will be next Wednesday, because the last class of our course. So the framework we're going to use is Network X, used for network analysis. So the, say, application of all this stuff will be social network analysis, which is the study of social structures using graph theory. And this is an area on the border of sociology on one hand and discrete mathematics on the other one, so mathematical methods and humanities. Vertices in a social network represent some sort of actors. So this could be people, could be social entities, something else. And edges, also sometimes called ties or links, they represent various relations between actors. So typical relation is friendship, but also there could be asymmetric stuff like subscription. Some person subscribes to a source of information, but the source of information does not interact with him itself and stuff like that. And the important thing about the social network is computing some parameters of the graph, and we'll see these parameters in action. So we're going to get acquainted with specialized software for working with such databases. And one of the ideas which I wanted to share in this lecture is that so in real social networks, some of the numeric parameters which can be computed for this graph are essentially different if compared to, say, a random graph. So the social network is a graph with a very specific properties, which is hard to model using statistical methods. And one example is this clustering coefficient we'll compute it today. So the idea of clustering coefficient is that, what is a clustering? There's a graph, and inside it there is a group which is like a clique. We considered last lecture, but it can be not a clique, it can be something like a dense subgraph. So the density of a graph can be somehow measured by this clustering coefficient, and it tends to be quite high. And this reflects the fact that if you have a person and there are his friends, then they are much more likely friends among themselves than just random people. On the other side, being highly clusterized, the social network happens to be tightly connected. This is represented by the following 6 degrees of separation, or 6 handshakes empirical fact, which claims that any 2 people in the world are connected in no more than 6 social connections. So any people in the world, so only 6 edges. In graph theoretic terms, this means that there is this parameter called diameter, and it should be less or equal than 6. So the diameter is just the length of the, so it's max min. So for any 2 vertices in a graph, you can compute the distance between them. This is the length of the shortest path, and then you take the maximal distance. So take the 2 most distant vertices and compute the distance between them. And in the social network, it's bounded by 6, which is really small given billions of vertices, billions of people. So in the exercises we're going to discuss, we shall use a real-life data set, which is called SNAP. What is SNAP? Is Stanford Network Analysis Project. So they provide this data. The data set is given just as a text file. It's not so big, so reading it from this file is quite easy. And this data set includes, well, it's a data set from Facebook, so from friendship relations on Facebook. And the data set we use includes friends of given 10 Facebook users. So these are called so-called ego networks. So there are 10 points, 10 people, and you take them, all their friends, and you take the friendship relations, of course, of these people with their friends, and also among those friends. So it's just a subgraph. Of course, this is not the whole, say, social network as it is, but well, the whole network cannot be used as a data set because even if it is anonymized, it could reveal personal data. And also you could have legal problems with stuff like that, with using this Facebook data. And also it's enormous, so you will have to use some, say, more powerful computational devices than regular computers to do this. But here it is as follows. So you have 10 people, you take all their friends, and you take the subgraph, which is given by these vertices. So you take the friendship relations of these guys, and you take these points among them also the relations. These ego networks intersect, so they took not just some random people, but they took people who some of them are friends with each other, for example. So there could be the interrelations. This makes, as I said, the data set relatively small and tractable for analysis. Of course, it's all anonymized, so the data is just all the vertices are given just by numbers. We'll see it. So now network X. What is network X? It's a Python library for graph analysis and visualization. It's free software, of course, released under BSD type license. It's capable of handling quite big graphs, so real-world data sets like 10 million nodes and 100 million edges and more. So it's really a thing you could use in practice, and it's highly portable and scalable. So this is the way you install it. Of course, the slides will be online, so what happens here, the network X is the library for the network X itself. Matplotlib and SciPy are used for visualization only. So in your homework number 3, you will not need that, but you can use them for visualizing something if you wish. Then you import it, of course, and I imported network X as NX just for brevity to use it easily. And then you can define a graph. So the easiest way is to define it manually. You just add edges one by one, and you see that you initialize a graph, which is called NX graph, and then you add edges. So the vertices are added automatically. If you have an edge, then it adds the corresponding vertices, and the vertices can be anything. It could be numbers, it could be strings of symbols, they're just markers for them. So this graph is by default undirected. So if you add edge AB, it's the same as adding BA. But you can also make it directed, or you can have multigraphs. So for directed graph, instead of just graph, you use dgraph, which is for directed graph. And also for multigraphs, you also have something specific, we will not discuss it. They could also be weighted, which means that each edge receives a number which is called its weight. An example is, say, I don't know, in roadmap, you can have capability of traffic on a street or something like that. This is the weight. So it could be, or it could be time or cost of driving along the road, for example. The weight is just added as an optional parameter to this add edge, so you can do it like this. Also, of course, network X is capable of reading graphs from datasets from files, because usually you do not read the graph just from do not just brute force the graph from in your Python code. You take it from some dataset. So in our example, we use Snap's Facebook dataset, as I said, 10 ego networks combined, and it is in the file Facebook combined.txt, and you will find the list of edges as pairs of numbers, as vertices are numbered. And you import it using NX read edge list method. So what can network X do? So network X we'll see it in our further discussion, that has convenient ways of computing something about the graph and stuff like that, but also, well, you see, graphs are abstract objects, but they have nice geometric representations. And you can see that using network X, you can visualize them, draw them on the plane. So it's helpful to see how the graph really looks like, and render an abstract graph to a picture is called a visualization. Network X is capable of visualizing graphs both in 2 and 3 dimensions. We will use only the first one. And it uses matplotlib. And it's called draw network X. And then you put it into a PNG file or SVG file. So this is a small example. It's the first graph we introduced. It's the output of network X. So you have 4 vertices and the following edges. You can see this exactly what we did here. This directed graph. You can see, maybe you don't see the arrows properly, but you see the small arrows here. This is an arrow, this is an arrow, this is an arrow. And between C and B, there is 2 of them. So from C to B and from B to C. And it got represented as sort of bidirectional arrow. But usually we draw it like 2 arrows like that. We may remove labels, because when we tend to have too many vertices in real life data, we do not have the opportunity to really draw it. And we'll see it on the next slide. So here we visualized the graph of the ego networks of the SNAP data set we're going to use. And here we see that you can see clustering. You can see how it clusterizes. So these blobs, these blue areas, they're actually hundreds maybe of vertices. So many of them, and we see that these are the connections between the clusters, and these are the clusters themselves. There should be 10 of them properly, because here we have 10 ego networks, but they are different. So some people have more friends, some people have less friends. If we can see these 2, for example, on the right, these are 2 ego networks, but there is a tight connection between them. And these are just some loose connections. So here you have only 1 connection. So this is probably an ego network, and here you have another ego network, and there's only 1 person who is a friend, say, who does this friendship to another one. So it means that, and you can see here how the social network really works. So it's highly clusterized. So there are groups of people which are tightly connected among each other. This is one thing. And the other thing is that it still has a small diameter, so there are still links between these clusters. This is how in real world it really works. So in a social network, as I said, vertices are users or people. The edges are formal friendship relations in the social network. And the probability for 2 random vertices to be connected is generally quite low. So if you consider all people in the world and just take 2 random guys, probably they do not know each other. They do not have a social connection in any sense. So meaning that they're not friends, they're not, say, acquaintances, not enemies also. So, but the other thing is that if, say, Alex is a friend of Bob and Alex is a friend of Carl, then the friendship relation between Bob and Carl becomes much more probable. So you can see it on the picture. So this is A, B, C. And the probability, given that it's so-called conditional probability, given that B and C are friends of some A, then the probability of friendship between B and C becomes much higher than it was originally for arbitrary random vertices. And this is the clustering, how you can compute the clustering. So the clustering idea is that if you are connected to something, then you tend to more probably to be connected among yourselves. And this is measured by the following global clustering coefficient. So you say that a triplet is a pair of edges going from one vertex A. So this construction is called a triplet. And for B and C, we don't know whether there is an edge or not. And a triangle is a triple of interconnected vertices. And you take the number of triangles and divide it by the number of triplets. You multiply this by 3. Because at each triangle it's 3 triplets, right? ABC, BAC, and CBA. So if the graph is, say, fully clustered, then each triplet should render into a triangle. But usually it's not the case. There are some triplets which are just like this, which do not have a triangle. And the more triplets give us triangles, the more clusterized the graph is. This is the clustering coefficient. This is why I multiply by 3, because each triangle includes 3 triplets. Thus, the global clustering coefficient is a probability for a random triplet to be closed. That means that B and C are connected. Also, a local clustering coefficient, where we count only triplets with given A as a central vertex. So suppose that degree of A is K, then the total number of triplets with A as the central is K multiplied by K minus 1 divided by 2, right? Because you take one of the, so you take vertex A, you take one of the K vertices connected to it, this is B, then you take one of the other, so it's K minus 1, it's C, and you divide by 2 because Bob and Carl are symmetric, you can solve them. And local clustering coefficients is the following ratio, so you take the number of pairs B and C for which there is a triangle ABC and divide by the total number of triplets. And this gives you the coefficient of the clustering one. Or like this. Sorry, it's some bug here, this division here on the bottom. So if A is an isolated vertex, then you cannot compute the clustering coefficient. It's because it's going to be 0 divided by 0, and it's for a good reason, because if you have an isolated vertex, what it means, well, you cannot, how does it cluster? You can say that it is, so there are 2 possible, say, borderline cases. The first one, you can say that it is not clustering, because it's just a guy who has no friends, so he has no cluster. But the other thing that maybe this one vertex can be viewed as an ideal cluster of itself. It is a complete graph with one vertex, so it's meaningless to ask for clustering coefficient here. So this is the visualization. For example, we have A. It is connected with 4 vertices, so Alex has 4 friends, and the blue lines are the interrelations among them. So they are quite likely to be also friends with each other, but not all of them. So these 2 are not connected, for example, on top. Then the local clustering coefficient is 2 divided, so it's computed by the following formula, because you have, so you have the number of edges here is 4, the blue edges, and here 4 multiplied by 3 divided by 2 is the number of triplets. So it's 2/3. It's quite a big clustering coefficient. So it's a clustered thing. See it here. And these are graph parameters. So you see that you can, what we already computed, we talked about the diameter of a graph, which is the maximal distance, local clustering coefficient, global clustering coefficient. You can also compute average local clustering coefficient. You just take the local LCC for every A, and then you just take the average, and so on and so forth. And these are graph parameters. So they are, you can find an analogy, for example, with statistical physics here, that consider a liquid or a gas, and what is a gas? It's, say, also billions of particles which go randomly, which have some random behavior. And of course, when you study physics, you do not try to trace each particle. You cannot do this. They go randomly. But you compute some macro parameters, which is like the temperature, the pressure, and stuff like that. And they're computed by some statistics over this gas or liquid or something like that. So the same thing we try to do for graphs when, say, they represent social network. So you have a social network, each guy is a particle, each person is individual, so that guy has his or her specific friendship relations, specific types of behavior and stuff like that. It's on one hand. And on the other hand, you can, so if you try to think about each person individually, you cannot do any study of the social network. But on the other hand, you can compute global parameters like the diameter of the graph, the global clustering coefficient, and stuff like that, which allow you to find out something about the graph without looking at individual nodes. So it's global statistical parameters. But of course, they do not give you all the information about the graph. So network X provides convenient interfaces for computing graph parameters. And the global parameters of the graph are basically just functions of it. For example, you can compute the average clustering coefficient, which is the average of local clustering coefficients, just by saying that you can take the graph, FB, it is our graph read from the database, from the data set of Facebook, and you just run this method, which is called average clustering. So next, what I wanted to talk about today is real versus random data. So this is a piece of code. Just I showed it on the slides in order for you to see how what it really means. So you import network X. Here we also imported random, which is just a function which gives you random numbers, the randomizer. We read is GFB is the real, the graph taken from a real data set, and we computed the average clustering coefficient and printed it out. Then we did the following. We here in this piece of code, which is the biggest one, actually there is a method of doing it in random X, in network X, just compute a random graph, but here we made it explicit. grand is what is called Erdős-Renyi random graph. So it means that we just take the number of vertices, and the number of vertices is the same as in the original graph. So basically we took the same set of vertices. And then we, for each pair of vertices, independently, we either draw an edge or do not draw it, with some probability. And the probability is also given the same as in the original graph. So for any graph, you can compute the probability of an edge, which is computed in a very easy way. You just take the number of edges which are actually in the graph and divide it by the maximal number of edges which are possible in the graph, which is nodes multiplied by nodes minus 1 divided by 2 is maximal possible number of edges. And here we construct a random graph with the same probability of having an edge between two vertices, but they are independent. So this Erdős-Renyi graph, where the fact that there is an edge between two vertices is independent for any pair of vertices. So we do it, we toss coins for each pair. And we do it here. So here what do? We take any vertex, then we take any other vertex, which with a number less than this one. And then we put the random edge. If the random gives you a number between 0 and 1. So saying this means that with probability edge probably at the edge. And we compute the clustering coefficient for the new graph, for the random one. And what happens? It gives us, the experiment gives us the following result. So this first line is the average clustering coefficient of the original graph. As you can see, it's quite high. Actually, something like what is 6/10 is like 3/5, right? So it's like similar to what we had here. We had 2/3, so it's bigger than a half. It's quite a big clustering coefficient. While for the random graph, it's really small. It's 100, 1 divided by 100. So it's a dramatic difference. So this means that unsurprisingly, the social network tends to cluster much more than the random graph, with the same probability of edge. So the number of edges, the density of edges is basically the same. You can see that this first line, the second line here, of course, it's random. So it's result of one experiment. But if you run the program several times, it will give you different answers, but it will still be something like that. So it will be still 0, 0, 1, and then something else. So it will not be 0.5, for example. Well, problem with overwhelming probability. So what does this show? It shows that one has to be really cautious with stochastic modeling of social graphs. And we've seen that in the examples of trying to model the pandemic of COVID-19. So you see that when you try some simple randomized model, like Erdős-Renyi, it will capture the same first parameter. The first parameter is the probability of an edge. But the second parameter, which is the clustering coefficient, will be not the same. And it's really important because the clustering in social networks, say in modeling pandemics, it means that how fast the virus will propagate and stuff like that. And unfortunately, this is the real issue. Question.
Why this happens? Like, why the clustering coefficient of the generated graph is so much smaller?
Yeah, this is the what we discussed here. So if you have two random vertices in a graph, then the probability that they are connected, this is low, right? But if you take two people who are connected to one, so if there is Alex and he has two friends, then the probability for Bob and Carl to be friends will be much bigger. But if you just take a random graph, it will not show such behavior. It will not capture it because this B and C, they will just have an independent. So the probability for B and C will be still the same, and it will be very small because social network. So in a social network, the general probability for two vertices to be connected is very low. It's sparse graph. But for this situation, the probability will raise, and this is exactly captured by the clustering coefficients. Okay, so also we can check 6 handshakes. Again, this is the function which is called diameter, and this you can calculate. It takes quite long because computing the diameter is you have to consider many pairs of vertices and compute the distance between them. This is quite time-consuming thing, and an hour data it yields 8. So it's not 6, but it's 8. Well, because we are not in the real network, but we are in the subset in the egocentric network. We can also compute distances. So by definition, the distance between two vertices is the length of the shortest path, and it's computed by the usual thing like that. And in directed graphs, this could be asymmetric, because the paths should be directed, and there could be a possibility that A to B is connected by a shorter path than B to A. There is a very important thing here that if there is no path, then you cannot run this, because it will not just say infinity, it will throw an exception. So it will return error. And to be on the safe side, you first have to check that there is at least one path while this method has path. So inside this network X, of course, there's much more. And when preparing for homework number 3, I advise to consult with network X documentation, which is of course available online. Many things which are useful for you can be found there. And now, well, here I wish you good luck, but before that I will show the assignment itself. So the assignment will be here. So here you see the web page of the course. What happened here since yesterday? We added home assignment number 3. So again, here you have the invite link to GitHub, the same way as in home assignment number 1. Again, you have the formulation as a README, which will also be copied to your repository. And the task is as follows. You will have this snap database, which is called facebook-combine.txt. It will be in your repository, so we don't have to download it from Snap, but if you want to look at Snap, it's also available here. You can, so you can find some things about it and more databases and stuff like that. So here's definition of ego network, and the task is as follows. You will be given a set of 11 vertices, and it is guaranteed that this set includes all 10 ego network centers, plus one extra vertex, which we'll call the imposter. And your task is to find out what the imposter is. And the detail that are here, you have to implement the function find imposter. This list of pseudo centers is the list of ego centers plus the imposter. It's edge list, which is obtained from the graph. And the tests automatically run this edge, read the edge list from Facebook combined, and perform these tests on your program with the vertices shuffled randomly. So this is done for just for the sake of, you can just find out what the imposter is and just manually somehow. But you cannot hard code it because in the tests the vertices will be shuffled. So this is basically the same. So the deadline will be next Wednesday anywhere on Earth, so it means next Thursday before 3 p.m. Moscow time. Invite link is here. Fallback solution, of course, is to the email, and everything else is the same as home assignment number 1. Also, recall that this Friday Saturday, we have the deadline for theoretical midterm, which is available here. And I also posted, which is what was the same as in the previous year, the grading formula. So here you have 1/2 of your grade which is given for the home assignments out of 10. So it's 4, 4, and the third is 2 because it's easier than first 2 homeworks. And the second half is for the exam. The final exam is obligatory for all the students. If you get half grades, I don't know, 6.5, using this formula, you'll get 7. So it's rounded upwards. But it's the only case it could be. Okay, the lecture slides for today are published here. So if any questions or comments on the home assignment, please ask them. If not, we'll continue further with some theoretical material examples. No, for 2 it's okay. It says scan or high quality photo is fine. So if for a home assignment number 2, you may submit it, you can type it in later or in Word or something else. You can typeset it, but it's not obligatory. You may just write it by hand or on, I don't know, some tablet if you do this, and save this as a PDF or some other file and submit it. The only requirement, it should be well readable. If not, well, then I will ask you to submit because even a high quality photo is okay, using a smartphone, for example. Okay, more questions? No? So now some more theory. Continuing what we discussed last time, it's algorithmic problems connected to isomorphism and subgraphs of graphs. So first, let us recall the notion of isomorphic graphs. So what are 2 graphs? What are isomorphic? How do you think?
One can be
Yeah, it can be mapped onto another. So the graphs like this, they look, they are drawn in a different fashion, but people see that they're essentially the same, right? And you can describe them both in a triangle and a quadrangle sharing a common edge. So it's the same graph in a sense, but of course, formally they are different. They're drawn in a different way. Sometimes the graphs look more similar, but they're essentially different. Because here you have this extra edge, which is connected to the quadrangle, and here is connected to the triangle. So they're essentially different graphs with probably different properties. And if you have isomorphic graphs, then all the graph parameters are the same. You can compute diameter, I don't know, any sort of clustering coefficients, anything else. For isomorphic graphs, they will be the same. So virtually it's one graph. And this is the definition. So they should have the same number of vertices. And you can make a one-to-one correspondence between them. So for example, you can number vertices of both graphs from 1 to n. And if vertices with the same numbers are connected in one graph, they should be connected in another graph, and vice versa. And they can be seen as different representations of the same graph. So for example, here you have G and H, and you can number the quadrangle 1, 2, 3, 4. Here also 1, 2, 3, 4. And for vertices 3 and 4, we have also a triangle with 5. For example, you have edge 3, 4 here. You have the same edge 3, 4 here. You don't have edge 1, 5 here. You don't have edge 1, 5 here also. And the isomorphism itself is the correspondence between vertices with the same number. So with this example, these dashed or dotted lines they form the isomorphism. So it's one-to-one correspondence, or as you said, bijection. So, algorithmic question. What is the algorithmic complexity of checking whether two given graphs, G and H, are isomorphic? How do you think? To what class does this belong? So you have the input two graphs, G and H, and to what complexity class does the isomorphism problem belong? P? Why?
Because we need to check, for example, we take first the one or map to the one.
Yes, exactly. So, of course, it belongs to NP. This is the upper bound. That one can non-deterministically guess the isomorphism. What you need to guess for each vertex, you need to guess to which it is going to be connected. And then checking that it is an isomorphism is really polynomial, right? It's routine. You say that you have to check that it is a bijection, that it's one-to-one correspondence. This is easy. And next you take each pair of vertices and check whether they are connected in one graph, if and only if the corresponding pair is connected in the other graph. This is quadratic time, right? So with respect to number of vertices, because the number of possible edges is quadratic. But one of you said that it's P. This is absolutely not obvious, because how can you find the isomorphism in polynomial time? Nobody knows. Probably you can, if you pursue this direction and find such an algorithm, you could get a very important prize. Because it's a quite rare species of an NP problem for which nobody knows both things. So there is no known P algorithm for it, polynomial algorithm. If you manage to do this, you could probably become very rich. But this is not hopeless, because on the other side, nobody knows that it is NP complete. So, even if P is not equal to NP, nobody knows there is an intermediate problem. It's, as I said, it's quite a rare situation. So in our previous examples, we had usually two possibilities. For example, we had two coloring and three coloring. Two colorability of a graph is polynomially decidable, right? And it's reducible to two SAT, and we know. Three colorability, it's NP hard, NP complete. We didn't yet prove it. We'll prove it today or next time in the practical class. So we know that the usual thing which people think about the NP class, that there are easy problems which are NP and relatively easy, and hard problems which are NP complete. This is an example of a problem for which we know neither. So it's something in between. It could be NP complete. It could be P. And in the case if P is not equal to NP, it could also be strictly in between. But nothing is known about that. So this is just for you to know that I gave this example. The example is quite trivial, but on the other side, it could be meaningful that you can check that two graphs are isomorphic algorithmically. It could be meaningful because this is a really interesting problem, but with no idea. It could be an NP hard or not. Now subgraphs, well, a subgraph is part of a graph which is obtained by taking a subset of vertices and a subset of edges. And the vertex subset should cover the edge subset. So if we take an edge in the subgraph, we should also take both its ends. So for example, this is a graph, and we took a subgraph. So we could say that we removed some edges and we removed some vertices. There is a specific kind of subgraph which is called induced subgraph, which means that we should keep off edges of the original graph if we keep their ends. So this is not an induced subgraph, because here we kept, on the bottom, we kept two vertices, but we removed the edge, we made it gray, right? So an induced subgraph does not allow that. And there is a dual notion of a spanning subgraph, which includes all vertices of the original graph, but may lack some edges. So this is a spanning subgraph, we kept all the vertices, we removed some edges. This is an induced subgraph, we just took vertices. And this is neither. So there is an algorithmic problem which is as follows, that given a big graph and a small graph G0, determine whether there exists an induced subgraph in H which is isomorphic to G0. So this is an important problem because it's a variant, this is a variant of pattern matching. You see a big graph, a big structure, and you want to find out whether this structure includes a specific small substructure. So for example, you could ask whether the graph includes a triangle, whether there is a triangle inside the graph. It's the standard algorithmic questions. Also, they're a variant of the problem without requiring the graph to be an induced one. So, yeah, as I said, yes, it's a search, a pattern matching problem, but for structures that are not words but graphs. Applications could be very different, let's say chemical or bioinformatics, when you try to find inside your big genome a substructure in a protein, for example. This stuff called graph mining, structure mining, where you have a big graph and you try to find something reasonable inside it, etc. And how do you think about the complexity of the problem? Well, this one is NP-complete. Of course, again, it belongs to NP. This is the same. You just guess this subgraph isomorphism. So you take H and you guess the subgraph which is isomorphic to G0, and you guess the isomorphism to G0. This is easy, but it's really NP-complete. Why? Well, because there are specific kinds of subgraphs. For example, the clique is a complete subgraph, right? So say a clique and social network is a group of users who are friends with each other. Independent set is an empty induced subgraph. So you take 4 vertices, for example, here, and their induced subgraph is empty. It's important that it is induced, because otherwise we just can remove all the edges. So the edges should not exist also in the original graph. And we showed that in set, for example, the problem of existence, an independent set of a given size, it's an NP-complete problem. It's a particular case of subgraph isomorphism. Therefore, independent set reduces to subgraph isomorphism. Independent set is NP-complete, therefore subgraph isomorphism is also NP-complete. Again, backwards reduction. So for graph isomorphism, we don't know whether it is polynomial or NP-complete or neither. For subgraph isomorphism, we know that it's NP-complete. Also, the same works for clique. It's one of the tasks of our exercises that clique and independent set, they're dual, they're mutually reducible to each other. And for clique, we do not have to require that the graph is induced, right? Because the clique is a complete subgraph and it's always induced. If we have a complete subgraph, then you don't have any other possible edges. So this means that the variant of the subgraph isomorphism problem where you don't require the subgraph to be an induced one, this is also NP-complete by reduction of clique. Another famous NP-complete problem is the existence of a Hamiltonian path. A Hamiltonian path is a path which visits each vertex of the graph exactly once. It's also a subcase of subgraph isomorphism. The question is whether it includes, as a subgraph, of course not an induced one, a chain of the number of vertices which is the same as the number of vertices in the original graph. So this chain is an induced subgraph, and this is a Hamiltonian path. If we have time today, we shall prove NP-completeness for Hamiltonian path problem. But first we'll sketch some applications in genomics. The other thing is an Euler path. In a multigraph, it is a path which traverses each edge exactly once. So it looks similar, but it's essentially different because the complexity is different. Finding a Euler path is polynomial, while even determining the existence of a Hamiltonian path is NP-complete. The same for cycles. So cycle is just a path which returns to the same point. But for specific classes of graph, the problem of finding a Hamiltonian cycle could be reduced to the problem of finding Euler cycle. So this is line graph. We say if we have a graph G, we can define its line graph L of G in the following way. So this is the original graph. Then you take its edges as new vertices, and then you connect the edges which have the common vertex. But I think something is missing here. Maybe not. So yeah, these are two connected. These are connected. Here have been connected, right? Okay, probably it's correct, but maybe there could be a misprint here. So yeah. So this new graph, which is called the line graph. Again, you take the vertices. The new vertices are the edges of the original graph, and you connect them if they have a common vertex. And the Euler path on the original graph induces a Hamiltonian path on the line graph, right? Because, well, just by definition, an Euler path traverses each edge exactly once, but in the new graph, the edge of the old one is a vertex, and a connection is exactly what we need. The converse, however, does not hold. In the new graph, there could be a Hamiltonian cycle which is not induced by an Euler cycle in the original graph. You can check this as an exercise. Here's an example. So here is a graph. This graph does not have any Euler cycles, right? But its line graph is the following one, and which has a Hamiltonian cycle. And of course, not every Hamiltonian graph is a line graph. So checking for this one, why a Hamiltonian problem is hard. It does not reduce to a Euler cycle in general. But sometimes, in some practically important cases, representation of a given graph as a line graph allows efficient construction of Hamiltonian cycles. And also, it could be defined for a directed graph. And again, same for directed Euler paths and Hamiltonian paths. Application: the genome and its fragments. So the genome is roughly a string of letters from the alphabet A, C, G, T, which correspond to nucleotides, adenine, cytosine, guanine, and thymine. These are basic elements of the monomers of the polymer structure of the DNA. And consider the following model situation, that the experiment, this comes from real, say, biological applications. The experiment does not give us the complete genome, but rather we have triplets. We have fragments of length 3 in some random order. This is given from just the say, biochemical apparatus somehow. And we want to restore this original genome, which is here. It's called reassembling the genome from the results. They could be not triplets, they could be, say, quadruplets or something like that, but the idea is basically the same. And how do we do this? Well, we construct the following overlap graph. So triplet U is connected to triplet V if the last two letters of U are the first two letters of V. Like CTA or the TAG. This is the graph of our triplets. And this is the Hamiltonian path. So we have ACT, then CTA, TAG, AGC, GCT, then CTG, GGC, GCC. Now we have reduced our reassembly problem to the Hamiltonian path problem. Well, it's great, but the letter isn't complete. And which would be much better to use Euler path instead. Fortunately, the overlap graph is L of G for another graph. So, for example, we have ACT, CTA, CTA to TAG. This is an edge which can be marked by CT, and this is an edge which can be marked by TA. And we introduce this new arrow here. And
sorry, with one common letter. Yes?
Yes, with one common letter, which corresponds to the CTA triplet. And we call this De Bruijn graph. And also we add the start and end, which is AC and CC, which we could know from some other source of information. And the Euler path in the new graph, which is called De Bruijn graph, which is basically the line graph of the original one, is it induces a Hamiltonian path in the overlap. And here we see that we're in the situation not of decision problem, but actually of a search problem. Because we actually know that the Hamiltonian path exists. We need to find it. We know that this was taken from a real genome, so this is really, there exists a path which will reassemble it. And our question is only to find its path. And here the picture how it works.
But it can be not unique, so that's
Well, if it's not unique, we're in trouble. Because this means that our information was insufficient. Here is an example. It has two possible ways to reassemble. What will be chosen? It's a hard question. Usually, this is just some of the DNAs are more, say, probable than others. Or you can, well, there are two ways of doing science, of course. The first way is just to run some machine learning and try to find out which is more, say, probable. The other one is to do some biological theory and try to find out. So, for example, you can try both of them and try to compute the protein which is defined by the DNA and find out which is a good protein or not. So it's biology. And this is an example that discovering the inner structure of a graph helps making the algorithmic problem simple. So the global problem of finding a Hamiltonian cycle is a hard problem. But here, or Hamiltonian path, sorry, it's not a cyclic structure. So problem of finding a Hamiltonian path is in general NP hard, but in some specific cases of application, you can see that we have specific graphs or specific settings in which the problems which we really need to solve are reduced to easier ones, say to Euler cycles, which are really easier to follow. And these De Bruijn graphs, or basically the line graphs, they really use the real-world genome assemblers. So this is really what is used. Of course, they do not try to compute the Hamiltonian path. They try to compute something easier. So again, the gist here is that you do the you have a hard problem. In general, it's hard, but in the practical life, you don't need really to use the hard stuff part of the problem, but you can reduce it to an easier one. And this is how, the good thing is that in many situations, how it works. I want to finish this part of the discussion by a quote from Grigory Skovoroda, a Ukrainian poet and philosopher, who said, bless the God who made hard things unnecessary and necessary things simple. So we still have some time, so maybe we can spend it for the proof of NP hardness of Hamiltonian path. If questions, then we are welcome to ask them. So this is a specific set of slides. They are additional. So we will not run any sort of exam, so don't worry. It's just for you to see how. So we have already seen a proof of, and so well again we're returning to NP completeness proofs. So the first and the basic NP hard problem was SAT, right? And it was Cook-Levin theorem, and it was hard to prove that it is hard because we had to reduce an arbitrary NP problem. Now we just do by backwards reduction. So we take a known problem which is already NP complete, and we reduce this NP complete problem to our problem. And this is the way how we proved NP hardness of 3 SAT by 18 reductions. We proved NP hardness of independent set or click on the previous lecture, right, by reducing 3 SAT to independent set or to click. Today we'll, at the practical class, we'll see the proof for 3 color. And this is the backwards reduction, because in the example to Cook-Levin, we proved forward reduction, right, that 3 SAT is reducible to 3 colors reducible to SAT, right? This is an example for Cook-Levin. It's not interesting because we know Cook-Levin, but there will be a backwards also. And how now we do it for Hamiltonian path. So we consider Hamiltonian path problem for directed graphs. For undirected, it will also be NP hard. It's just easier to follow the proof for directed graphs. And by the way, our example for genomes, it was directed graph, so it's okay. So given a directed graph and two vertices, S and T, so S for start, T for terminate, we ask whether there exists a Hamiltonian path from S to T, so a path which traverses each vertex exactly once, including the start and end. This problem is denoted by Ham path. Ham for Hamiltonian. Theorem is NP complete. We already know that it belongs to the NP class. And the NP hardness is the interesting thing. And we reduce 3-sat by Karp polynomial reduction to Ham path. I'm speaking fast here because it's things we already know. So backwards reduction means that you have a 3CNF phi, so it's Boolean formula which is in 3 conjunctive normal form, and we construct a directed graph called G phi with the following property, that G phi has a Hamiltonian path from S to T. S to T are designated vertices of this graph, if and only if the formula is satisfiable. It's the same as independent set, as you remember, right? So for independent set, we also constructed a specific graph which somehow encodes our CNF. For independent set, it was easy. Here it will be harder. We'll see how it works. And this is a specific graph which is called a gadget. So suppose phi includes m clauses. And for each variable, we construct the following graph which is called a gadget. So here you see that it has its own start and terminating point. It will not be the global S and T. It will be the local ones. Then the gadgets will be connected in a sort of polymer structure. We'll see how it works. And here we see that the source has links to these two specific vertices here. And inside we have two M vertices which are called U1, V1, U2, V2, UM, VM, which are interconnected in both directions. And then these first and last vertices, they are connected to T. But the middle ones do not. This is a gadget. So how can you traverse this gadget using your Hamiltonian path from Si to Ti? Well, there is the red route and the green route. So the red route goes to the right, then it traverses everything in the middle, goes backwards, right? Or you can go to the left and then go symmetrically. And they're the only two ways of traversing it in a Hamiltonian way. So because you have to start either left or right, but if you go, say, left, if you go down, you fail because you miss the vertices in between. So you have to go through this central point. And green will mean that, so recall that this corresponds to a variable xi. You will have, for each variable, you will have a specific gadget. And we'll say that if the xi is true in our assignment, then we choose the green route. If it's false, we will choose the red route. Because this is how we encode in our Hamiltonian path. This will be the way how we encode the satisfying assignment. And next, for each clause, Cj, we will have a designated vertex, Cj small, which will be connected to the gadget like this. So from Uj, you go to Cj, and then go backwards here. If this Cj includes xi. So what does this mean? This means that this extra vertex, which is outside the gadget, so it's one for the clause. Each gadget will be, if the gadget is the clause includes this variable xi, then the corresponding gadget will be connected in this way to the clause, right? So if it includes xi, then we add it in this way. What does this mean? That means that this new vertex can be traversed on the green route, right? So this is the green route, and this is the direction of the green route, right? So instead of going from Uj to Vj immediately, it could go through the tour to the Cj. And if it includes the negation, then it goes backwards. So from Vj it goes to Cj, and then back to Uj. So this means that this could be traversed only on the red route through the gadget. This is like this. So Cj should be visited exactly once. So we have to satisfy at least one of its literals. So at least in one, and actually only in one gadget, we have to visit Cj, which means that the value of the corresponding literal should be true. So if xi is true, then we will visit it on the green route. If the variable is false, then we will visit on the red root. And finally, we connect the gadgets. So here we say that this is Si, Ti. Ti will be the same as Si plus 1. Si will be the same as Ti minus 1. The first S will be the global S. S1 is S, and Tm or Tn is T. So we put these gadgets one upon another. I didn't draw this picture because, well, it's very big. And these will be connected by these roots to these CJs. And CJs are global. They are the same for all gadgets. And there is a Hamiltonian path from S to T in this graph if and only if phi is satisfiable. Indeed, suppose phi is satisfiable. What does this mean? This means that inside, so suppose phi is satisfiable, there's a satisfying assignment. Then what we do? First, we do not think about these CJs. We just think about this stack of our gadgets, right? So we have first, second, third, etc. It's okay. Then we traverse them. If so, each gadget corresponds to a variable. If formula is satisfiable, then in the satisfying assignment, the variable is either true or false. If the variable is true, we go through a green route. If the variable is false, we go through the red route. This is a path. It's still not Hamiltonian because we also have these additional vertices which were not yet visited. But now we recall the fact that this was a satisfying assignment, which means that each clause was satisfied. What does it mean that the clause was satisfied? It means that inside this clause, it is a disjunction, there is a true literal. If this literal is xi, a positive one, what we know? We know that xi should be true. This means that in our path, xi was traversed in the green way. But there is a green path here, and we could add a detour through Cj and visit this vertex also. And we do it only once. Even if there are several literals which are true, we just pick one of them and use it for traversing Cj, because we have to construct a Hamiltonian path. Dually, if we have Cj which includes the negation of xi, and this negation is true, this means that xi is false. This means that in our path we traversed the ith gadget using the red route, and this means that we can amend this path by adding a detour to Cj. After adding all these detours, we will have a Hamiltonian path. So a path which goes through all the gadgets and also visits all these extra vertices for clauses. And everything like that is done exactly once.
So in this gadget we have also, we may have several CJs.
Yes, yes.
But we may, like...
Well, some of them are visited, some of them are not.
Yes, okay.
Yes, exactly. But each CJ should be visited exactly once. So this is the trick. So this is one direction of the argument. There should be another one, because it's if and only if. Now, if we have a Hamiltonian path in G phi, we need to show that the formula is satisfiable, right? So now we have a path. This path should traverse all the gadgets, right? Also inside we could possibly visit these CJs. This could be also a problematic situation when you go to CJ from one gadget and return to another gadget. But it's easy to see that then you will ruin the path, Hamiltonian path. You see what happens, right? Because this CJ is connected to several gadgets. Could be connected to several gadgets. Question?
How are gadgets connected with each other?
I'll show this like this. So the first one is the starting, then the start of the second is the end of the first, and etc.
So you just put it in a row.
Yes, yes, yes. So the problem could be if you say come from, I don't know, uj, and then you return to some other vj, which is in another gadget. But this is, of course, you cannot complete that, because this vj could not be visited in any way. So this is the question.
what is CJ? Why recruited and what are UJ and VJ?
Oh, well, CJ is a new vertex for each clause, for clause number J.
So CJ represents a clause.
A clause, yes. And
it is junction.
Yes. And it's outside all the gadgets. So and the UJ and VJ are the corresponding vertices. So you see that here you have the number of vertices, which is the same as the number of clauses. So this means that if you have a good Hamiltonian cycle, then it should traverse CJ in a good manner. So it goes through UJ here, goes here, and then goes backwards to the same gadget. Otherwise, it's easy to see that the Hamiltonian path could not be the Hamiltonian one. It will clash. And this is okay because now we see that each Hamiltonian path traverses all the gadgets one by one and visits also these CJs, the clauses. Now we look at the directions how it traverses these gadgets. So either to the right or to the left, either green or red. If green, we say that this variable should get the assignment 1. If red, we give the assignment 0. And then we check that it is really satisfying assignment. For each clause, the clause was visited at some point. As it was visited, this means that the corresponding gadget was traversed in the correct way. So for example, if CJ was visited in this gadget, this means that XI was true, because we could only visit it on the green route, and CJ includes XI, so the clause is true. And dually, if it was visited in this way, vice versa, then it was visited on a red route, the clause includes not XI, and the ith gadget was traversed on the red route, which means that the clause is also satisfied. And this for any clause.
But if we visit these two CJs in one gadget, can we make this?
It's okay. Then it means that both of them included. So, for example, if you visit it on the red route, then both includes not XI, and both are satisfied by this gadget. It's
but,
okay.
Then we need to go visit them in that.
Yes, yeah. But now it is given because we know that this is a Hamiltonian path. Now it's the other direction. We know that the path is Hamiltonian. We didn't visit it in another gadget because each vertex is visited exactly once. Okay. So, well, the proof here is quite routine. If you missed some of the details now, it's okay. You can restore them on your own. The really tricky thing, and it's a matter of, I don't know, creativity, at least, is how to find such gadgets, how to find this reduction. And you see that if in the independent set problem it was quite natural, the encoding. Here the encoding is, well, it's easy to explain when you know it, but these all were great, say, scientific results. How to prove NP-completeness of something. And this is a sort of dual, say, side, the dark side of computer science. The light side is when you prove that something is solvable, you construct algorithms. Dual, the dark side is that you prove that something is hard. And for this, you invent reductions, which are also algorithms. Because, well, of course, all this stuff is constructed in polynomial time. I didn't say it, but it's of course. So you introduce an algorithm, quite an involved one, with specific data structures and stuff like that, and this algorithm doesn't solve anything. It is never used. It is only never used, I mean in practice, never run on the computer. It's used just to show that something is hard. So this is the dual thing, which people sometimes call this thing theoretical computer science. Of course, theoretical computer science is a very big term, which includes many stuff like that. But complexity theory is one of the core disciplines there. Why it's called theoretical computer science? Because the strange people who invent algorithms which were never going to be implemented, the reductions. So these algorithms are not going to be run. They're just used for proving that something is hard. Because if you try to run it, what it will give you? It will give you that you have a CNF, and you can check satisfiability of a CNF by reducing it to find a Hamiltonian path. but you don't have a good algorithm for finding Hamiltonian path anyway. So for SAT is even easier for SAT solvers. So this is just for proving that it's hard and people should seek for easier things. Okay, so I think that this is the time to finish the lecture and reconvene at the usual time for the seminar class.